Hello, chemistry people. In the last video, we talked about performing a stability analysis using explicit differencing. In this video, I want to take us through an implicit differencing method on the heat equation and then use that to perform our stability analysis. So, start off by pulling up the old iPad here. All right. Awesome. So here's our prompts. So we're going to use what's called a Crank-Nicholson differencing method, which, like I just said, is an implicit method. And performing the stability analysis, we'll be able to see that this is actually going to give us more possible values for our value in our heat equation. So let's start off by remembering what heat equation we derived in the last video, which is going to be the change in temperature with respect to time is going to be the constant alpha times second derivative of temperature with respect to position. Now, what Crank and Nicholson did back in the day was they decided to use, basically they came up with a method of implicit differencing that uses both the backward and the forward of the Euler differencing that you were probably taught in your ODE class. And by averaging those two, we can find our second derivative. So what does that mean? Basically, we're going to evaluate this guy here from t to t plus delta t, right? And to do that, we're actually going to take two differences and then average the difference in those differences. So let's see if we can do this here. On the left-hand side, it's going to look very similar to last time, except that we're going to be changing our position as well, I believe. Actually, wait, let's not change our position. Let's do the exact same thing, because this is just a first derivative, so we don't really have to worry about the double differencing as much. However, on the other side, we are going to take an average. So what is an average? It's going to be divided by 2 in this case, because there's two differences that we're looking at. So we'll go ahead and divide our alpha value, which is going to remain constant, by 2 here. And then we're going to multiply that by the difference of the first term over delta x squared minus another difference over delta x squared. And what are these differences? They're just going to be the differences that we came up with last time, except we're going to use two different time steps as well here. So remember, the generic form was kind of an accumulation of 3 positions at one certain time. But we're going to do this exact same positioning difference for 2 different times. So this time will be n, and this time will be n plus 1. Okay. And so that is really what Crank-Nicholson differencing is. It's simply, let's average it over 2 time steps here, right? And you can see how this was pulled right out of the explicit differencing, except this time, instead of just going in one direction, we're taking a backwards direction. So this would be kind of our backwards direction here. And then this would be our forward direction, right? Awesome. So that takes care of part 1 here. And part 2 is, of course, let's see if it's stable. And the problem already kind of gives us the hint that regardless of the choice of R, we are going to see stability in this situation. So let's go ahead and do that. Remember last time, what we did to perform the stability analysis was created that R term. So let's go ahead and start by doing that. We'll say R is equal to alpha delta t over delta x squared. And so that's just pulling the delta x out from there, and then multiplying over by delta t. So let's rewrite our equation here. Let's actually put all of our n+1 time steps on the left and all of our n time steps on the right. So that'll look something like this. Let's see, all of these are n+1, so they will get subtracted over. Times. Okay, let's double check our arithmetic here. Sorry, not arithmetic, algebra. And what our algebra says is, yeah, that looks correct. Oh, there's one thing wrong. So this should really be r over 2, right? Because, of course, we didn't define r with that 2 in the bottom there, right? Because it wasn't in the bottom last time. So technically, I guess we could simplify this into, well, this would be 1 minus r over 2 of u. Oh no, it would be 1 minus r. Yeah, so we could do this to it if we wanted to. Uj n plus 1 minus r over 2 uj plus 1 n plus 1 uj minus 1 equals something very similar on this side, right? Oh, this should be a plus because it's an average, right? We're going to add the two terms and then divide them, not subtract the two terms and then divide them, which would mean that this should really be a plus. Okay, yeah, now we're in business. Minus r over 2 uj plus 1 n uj minus 1 n. Awesome. So now we've got our equation here. And really, this is probably the proper part to end part 1. But this was just all simplifying algebraically the initial equation we came up with here. So now we want to go ahead and assume the answer from on moment stability, right? Last time we defined error and then said that's going to be equal to u, and then set error equal to amplitude as a function of time, as well as e to the imaginary number k, j, delta x, right? And so that's exactly what we're going to do here. I'm just going to skip this step of writing error into the equation again, and simply going to write in all of the amplitude terms immediately. So let's go ahead and do that. And again, our goal here is going to be to solve for an a n plus 1 over a n, right? Because that's going to be our gain term, and then we want to bound that gain term, right? So all that being said, let's try it. So 1 minus r, a n plus 1, e I k j plus 1. And anytime we have e, just like in the last video, a, j, delta x, e, I, k, delta x is the same as e, I, k, j plus 1 delta x, right? So that's just an exponential identity that we can go ahead and write here. E, I, k, delta x. Yeah, okay. This is 8n plus 1, 8, okay. Yeah, back to algebra. All right. So then we want to do all of that, kind of take this space out here so that we still have space to try and solve this. Minus r over 2 times a to the n plus 1, e to the I, k, j, delta x, e to the I, k, delta x, plus a to the n plus 1, e to the I, k, j, delta x. Now this one's negative. So a to the n minus 1, remember, is a to the n, a to the negative first. So e to the negative I, k, j, I, k, delta x, right? Okay, second, the right-hand side of the equation then, 1 minus r, u to the j to the n would be a, n, I, k, j, delta x, minus r over 2, no, plus r over 2. A n plus 1 e I k j delta x e I k delta x plus a n plus 1, but n, we should just be n too. Just run the right hand side now. E to the I k j delta x e I k x plus, nope, that's it. Round it off. And we're done. So you can see basically all of the difference in here, besides the ends, is of course the plus and the minus sign, right? Yeah. So what are we going to do? Factor out e, I, k, j delta x, right? That exists everywhere. So start by dividing that off. Okay. And then, again, what we're solving for is a n plus 1 over a n. So then from the left-hand side, can we go ahead and factor out an an plus 1? Let's see. So again, we're just looking at the left-hand side here. An plus 1 times 1 minus r e I k delta x minus r over 2 e I k delta x plus negative I delta x. And that's it. So then same, it would be virtually the same thing on the right-hand side here, except we just flip the sign. Oops. Break this down a bit. And here. Except all we do here is go ahead and flip this sign to a plus. Awesome. And of course, this would just be an. Good deal. So then, a n plus 1 over a n equals, well, 1 minus r e I k delta x minus r over 2 times e I k delta x plus e negative I k delta x over 1 minus r e I k delta x plus r over 2 e I k delta x plus e negative I k delta x, right? And that is, of course, our gain, G there. Now, of course, we should be able to recognize e negative I k delta x plus e to the positive I k delta x is the same as 2 cosine k delta x. So, from all of that, we can rewrite gain as 1. I want to take that guy out too. So a little bit of manipulation here. We can say 1 minus r plus r cosine a delta x over 1 plus r minus r cosine a delta x is our gain function. Yes. Right, because again, we're dividing by 2 there. And that's why we're getting to r. So, okay. I think all of that makes sense. Yes. Okay. I think that all looks good. So then, what are we going to do to our gain function here? Well, again, we're going to bound it by saying it has to be less than or equal to 1, right? Absolute value-wise. Well, of course, we can go ahead and start to manipulate this here. So what we're really doing is, well, if we want to make the bottom 1, we have to multiply both sides by the bottom. So we're really saying this is less than or equal to 1. 1 times 1 is 1, 1 minus r, plus r cosine a delta x, r times 1 is plus r times plus negative r squared plus r squared cosine a delta x. Then we have negative r cosine a delta x plus r squared cosine a delta x minus r squared cosine squared a delta x. So then, of course, r and r cancel, r cosine k, r cosine k. You might guess that one of this guy plus r cosine k delta x came here. That's right. Plus, okay. So that all simplifies to, oh, these r squared should cancel too. Now we're simplifying to 1 plus 2 r squared cosine a delta x minus r squared cosine squared a delta x less than or equal to 1. And subtract 1, so now we're at 0. It's less than or equal to 2r squared cosine k x minus r squared cosine a delta x. Feeling like I missed something here. Let me look at this for a second. Well, maybe this is still right. Because you would factor out r squared here, 2 cosine k delta x minus cosine squared k delta x plus 0. This is bounded by -1, and this is bounded by 0 and 1. So maximally, you would get 1 minus 1, which would give you 0, and thus the equation holds true. At max conditions, you're getting 1 minus 1 equals 0 on the inside, and thus value of r doesn't matter. Minimally, you're getting -1 minus 0. Yeah, but we're only worried about the max condition. Okay. So thus, we can never get a value of r that will exceed that condition there. Yes. Because what we should have carried is that -2. Okay, yeah. And then when we subtract over, this should be -1, -2. There we are. Okay. I forgot my absolute value signs. But thus the condition holds that for any value of r, so for all r in, sorry, get my math, for all r in negative infinity to infinity, this equation holds true, right? So thus, we've proven here that any value of r we choose is stable. So what does that look like? Because on our last simulation, we had written it as such that obviously the discretization didn't work in this way. So let's look at a simulation again, what part 3 is, and see that we can put r all the way to 2, run it for 2,500 time steps, and then plot the simulated results. So let's go ahead and do that here. So here's our conditions from last time. And we can see that, oh, my face is kind of annoying. Here, I guess. We can see that as our R value, if our R value is even 1/100th larger, we get massive oscillations in an unstable system. So let's try this again with our explicit differencing method. This time, we are going to make a larger R value. Yeah, let's try this. So we are going to need to create a matrix here of our, it's going to be easiest to create a sparse matrix of our temperatures here for the different positions. So by doing that, we can use a different formula called solve banded, and that I think will solve our matrix equation. So let's start coding it out, and then I'll go ahead and run our import here. So again, let's make a bar, discretize it to 100 steps. And again, our U matrix is just going to be a matrix of that many steps and 20 unknowns. Well, this is our middle temperatures, right? So then we can say U, how do we want to do this? So I guess we want to define our boundary conditions in some way, right? So UL for left is going to be 50, and then U on the right is going to be 80. Use dots because last time I screwed us up. And so then what we're going to do is we want to make that matrix now. So let's just call it A, because remember the generic matrix equation is going to be AX equals B, right? So it's going to be what? Well, what we're going to want to do here is we're going to want matrices of the Crank-Nicholson terms that we just found. So our formula here is going to be, now let's see, we want to split up this equation. We want a matrix of our coefficients and then a matrix of our what is our x here? That's the question, right? I know A is going to be our coefficients. We should be solving for X. And what are we solving for? We're solving for temperatures at different times for each position. Okay. So let's go ahead and try this. So we want an array of our coefficients. So what would our coefficients be for each term here? For our first term, it should be let's see. We're going to concatenate. We want 100. This is each position at our first term. This coefficient is negative r. Okay. Then we want an array of n where our coefficient is 1 plus 2r. And then we want an array that looks exactly like the last one. Okay, that's A. Let's go ahead and try and plot this. Actually, this is going to be plot 2. Plot 1 is above. Okay. Add our scatter here. X is going to be our position again. And that's the same positions in the last video. And Y is simply going to be our, this is for time 0. Should probably specify that. Time 0. But time 0, we just need to concatenate the rows of U of L, and then U, and then U R. Right? And then those is going to be equal to lines. And we can name it F string. Okay. Now we need our loop. And so what our loop is going to do is solve for our new temperature given the vector of solutions, but the solutions are going to change for each iteration, right? So the solutions are what was the time at the last step, right? Yeah. The time at new step equals what times coefficients. Okay, let's try this. For I in range running for 2500 is what the problem statement gives us. Okay, B equals 1 minus 2 times R, and then we're going to multiply that by U. So that's all of our middle values, right? Then we want to find our middle values here. So to change them, what we want to do to them at each step is have R multiplied by U. What do we want here? So this is what's happening to all of our values. We're going to need influence from the left and influence from the right. So influence from the left would be 2 onward, and then we should also be influencing from the right. So plus equals R times U to 2, right? Let's see if that works. And then our first position, of course, to that, we want to add the influence from its right and its left. So its left would be U of L, and then its right would be, well, the influence on that would be what? It should be 2 times R times. That's what our equation gives. Right? And then plus R times U. So what's on the right? 1. Okay. Same thing for the last value here. We're going to give it influence from its right. So influence from the right is just R times U right, plus influence from the left is 2 times R times U. What's on the left? 2, I guess, right? Okay. Now, we want all of this to influence the new U value. So suppose U equals. So this is where we have to use the import function here. So I think it's called solved, but I do not remember what library it is in. Scipy.linalg. Okay. From scipy.linalg import solved. So it simply, this function simply imports, maybe, show me. Should be importing part A. I'm going to give me the input here. And then B. Now let's put solve into imports here. Just giving it to me. L and U is first. Where are L and U? Number of non-zero lower and upper diagonals of our matrix. So in this case, our upper and lower diagonals should just be 1 and 1. Right. Okay. So we've done this a bunch of times. So we only want to plot if the last time we did this, we said I mod is 1,000. So this time we're running it, let's say 25 plotting points. So then again, y is just going to be the exact same thing that we did last time, right? It's going to be our left, and then our u, and then our right values. Mode equals lines, and let's give it a name of f string. Update the layout here. Width equals 100, height equals 400, and template equals lovely. Sorry. All right, let's try it and see what happens. It's stopped. And I've got to try here. Oh, we need to define R for this system, I guess. We're running R as 2. Oh, I didn't run this up here, so let's just copy this down. Okay, so we have an indexing issue first. Oh, that's because I'm running only to 2 instead of. Okay, A and B are not compatible. Okay. Let's look at the shape of A then. Shape A. Let's toss all this in another cell. Okay. Yeah, just see there's a problem. Is that we need to actually transpose this. Yeah, that's right. Let's see if it runs now. Okay. So a little bit of coding wizardry on the back end there. But we did get it to go ahead and run. Again, we see it looks very similar to our, it would if I had run this with an R value of 5, right? Fine. Okay, I took something out of here, and that's why this one's running weird right now. Run that and then run that. Okay. We can see that graph actually looks quite similar to this one. The difference is, of course, that the response time of this one's going to be a little bit faster because we have a faster R. So we're discretizing it a little bit nicer than we would be on the other one. Which means simply that our delta x squared is potentially smaller than our delta x squared on the first one, right? So remember how we defined alpha? We defined it as, we said alpha was equal to, sorry, how we defined R is equal to alpha times our delta t divided by our delta x squared, right? So as this ratio improves, right, meaning say as R gets bigger, that means our dx squared is getting smaller, and then potentially we're having this counteract the smallness of this. So what would be better is if we could actually, if we could model just this dt over dx squared as one term and alpha is a different term. Obviously, alpha is more material dependent. But assuming we're using the same material here in both of these scenarios, then our second model is showing us a better ratio of dt to dx squared. And thus we have a faster response of the system, right? All right. That is all for this one. We talked about stability and kind of how we numerically define that, and then differencing techniques, as in once we've developed a partial differential system for a partial differential equation system, I should say, for a process, then how do we take that and linearize it to then give us an algebraic way to manipulate it and then simulate it? As we go further into the course, we're going to talk about how we take that linearized differential equation and we can actually use different techniques to find stability in a better way than simple simulation